March 29, 1944, Venegono Airfield, northern Italy. The Consolidated B-24 Liberator sat at the end of the runway, its 4 Pratt Whitney engines silent, propellers motionless in the afternoon light. Luftwaffe ground crews circled the bomber cautiously, as if approaching a sleeping predator. The aircraft looked intact, no visible battle damage, no fire scars, no holes torn through the aluminum skin. Just an American heavy bomber that had developed engine trouble over northern Italy, forced its crew to bail out, then glided into Italian territory and landed itself in a field near Milan. The pilot had set it down perfectly before jumping. Now it belonged to Germany. Oberleutnant Klaus Hartmann stood beneath the port wing, running his hand along the fuel tank's access panel. He'd been summoned from Rechlin, Germany's primary aircraft testing facility, specifically to evaluate this capture. His orders were clear. Examine every system. Document every specification. Determine what made American bombers so difficult to destroy. Hartmann had test-flown captured Allied aircraft before. Spitfires, Mustangs, even a B-17 Flying Fortress that had landed in Denmark with mechanical problems. But the B-24 represented something different. American factories were building these bombers at rates that defied German intelligence estimates. More than one every hour at Ford's Willow Run plant alone. 18,000 would be produced by war's end, making the Liberator the most produced heavy bomber in history. The question that haunted Luftwaffe fighter pilots wasn't how to shoot down a B-24. It was how to keep them shot down. German pilots reported hits that should have been fatal, cannon shells that punched through wings where fuel tanks sat, yet watched American bombers continue flying, limping home to England on 3 engines or 2, trailing smoke but not flame, refusing to explode. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The self-sealing fuel tank was no secret. German intelligence had known about the technology since 1940. The British had fitted them to Hurricanes and Spitfires during the Battle of Britain. American bombers incorporated them as standard equipment by 1941. The principle was simple enough to understand. Layers of rubber and fabric surrounded the fuel cells. When a bullet pierced the tank, fuel seeped into these layers. The untreated rubber layer absorbed the gasoline and swelled, sealing the puncture within seconds. Simple in principle, impossible in practice, at least for Germany in 1944. Hartmann opened the wing access panel and stared into the fuel tank cavity. The rubber bladder inside looked ordinary at first glance. Black synthetic material, slightly flexible to the touch, suspended within the wing structure by web straps attached to a hard fiber ring. But the engineering behind this seemingly simple component represented American industrial capabilities that Germany could not match. 2 test pilots arrived the next morning, ferried in by a Fieseler Storch liaison aircraft. Their mission was to fly the captured B-24 from Venegono to Rechlin for complete evaluation. But first, Hartmann needed to examine what German fighter pilots were shooting at and understand why it refused to burn. The B-24's fuel system consisted of multiple tanks distributed throughout the aircraft. 2 main wing tanks held over 2,000 gallons. Additional wing tanks could be installed for extended range. Bomb bay auxiliary tanks brought total capacity to over 3,000 gallons when fully configured for long missions. Each tank was not simply a metal container filled with gasoline. The B-24's self-sealing fuel cells represented years of American Rubber Company research, millions of dollars in development costs, and manufacturing, techniques that required materials Germany no longer possessed in sufficient quantities. Hartmann began his inspection methodically. He measured the rubber layer thickness, 1 inch at minimum, sometimes thicker. He examined the laminated construction. Outer layer of vulcanized rubber, impervious to fuel. Inner layer of untreated natural rubber that would swell on contact with gasoline. Middle layers of fabric reinforcement. Additional layers of rubber compounds with specific chemical properties that prevented fire propagation even when bullets generated sparks on impact. The engineering specifications became clear as he documented each component. The self-sealing material reduced fuel capacity by approximately 23% compared to unprotected metal tanks. For the B-24, that meant sacrificing roughly 500 gallons of range to gain survivability. American planners accepted this trade-off without hesitation. They could build bombers faster than Germany could destroy. Loam. Losing fuel capacity mattered less than losing trained crews. But the material composition told a different story, one that explained why Germany couldn't simply copy what they were examining. Natural rubber, untreated, high-quality latex from Southeast Asian plantations. The outer layer required tons of it per aircraft. Germany had been cut off from natural rubber sources since 1941, when Japan seized control of British Malaya and the Netherlands East Indies, regions that supplied 77% of the world's natural rubber production. Germany produced synthetic rubber, Buna types developed by I.G. Farben, from coal and limestone. It worked adequately for tires, belts, and hoses, but synthetic rubber lacked the specific swelling properties needed for self-sealing fuel tanks. When exposed to gasoline, Buna compounds did not absorb the fuel and expand quickly enough to seal bullet holes before fire started. American rubber companies, Firestone, Goodyear, B.F., Goodrich, U.S., Rubber, had spent years perfecting formulations that worked. They tested materials against 50 caliber bullets, 20mm cannon shells, even armor-piercing incendiary rounds. The final designs could withstand multiple hits, seal punctures in seconds, and prevent fuel vapor explosions that would blow aircraft apart in mid-air. Germany's synthetic rubber could not duplicate these properties, not because German chemists lacked skill, but because the molecular structure of Buna rubber fundamentally differed from natural latex. You could not engineer around the problem using existing German materials. You needed access to plantations in Southeast Asia, controlled by Japan, separated from Germany by Allied naval blockades that made shipping impossible. Hartmann wrote his preliminary findings in language stripped of diplomatic hedging. The B-24's self-sealing fuel tanks cannot be replicated using available German materials. Synthetic rubber lacks necessary absorption and swelling properties. Natural rubber required for proper function is unavailable in quantities needed for aircraft production. The evaluation team began preparing the Liberator for its flight to Rechlin. German markings were painted over American insignia. Fuel was loaded, engines tested. The B-24 would fly north to Germany, where Luftwaffe test pilots would put it through comprehensive performance trials. But Hartmann already knew what the final report would conclude. American bombers weren't surviving because of superior armor or better tactics. They survived because American industry could produce materials Germany could not, in quantities Germany could never match, using resources Germany no longer controlled. The morning of April 1st, 2 Luftwaffe pilots climbed into the B-24's cockpit. They had no flight manual, no training on American systems, only experience and intuition to guide them through the startup procedures. The 4R-1830 engines coughed to life, propellers biting air, the bomber shuddering with power. It lifted off from Venegono without incident, climbing into Italian airspace, then turning northeast toward Munich and eventually Rechlin. The captured bomber would provide Germans with valuable intelligence about American construction methods, operational systems, defensive armament. But it would not solve the fundamental problem that kept B-24 seconds flying home after taking hits that should have been fatal. Inside those wings, suspended in hard fiber mounting rings, the rubber bladders represented an industrial capacity Germany had lost long before the first Allied bomber crossed into German airspace. Every self-sealing fuel tank required roughly 30 pounds of natural rubber, carefully formulated into multiple layers with specific chemical properties. Building 18,000 B-24 seconds meant sourcing over £500,000 of natural rubber just for fuel protection systems, separate from rubber needed for tires, hoses, oxygen masks, and thousands of other components. America possessed that rubber. Germany did not. The mathematical equation was brutal in its simplicity. When the B-24 touched down at Munich Riem for refueling, Hartmann's preliminary report had already reached Berlin. Technical intelligence officers read his findings with professional detachment. Nothing in the report surprised them. They had examined captured British fighters equipped with self-sealing tanks back in 1940. They knew what the technology required. They knew Germany couldn't build it. The question wasn't whether Germany could copy American fuel protection systems. The question was why American industrial planners had accepted a 23% fuel capacity reduction to protect aircraft that would fly into combat, knowing many wouldn't return. The answer lay in mathematics that German strategic planners had miscalculated. America could build more bombers in a month than Germany could destroy in 3. Training programs graduated more replacement crews weekly than Luftwaffe fighters could shoot down. Self-sealing tanks didn't need to be perfect. They just needed to save enough aircraft to maintain numerical superiority that made individual losses statistically irrelevant. One B-24 shot down cost America approximately $200,000 and 10 trained crew members. One B-24, saved by self-sealing tanks that prevented fire, meant those crew members lived to fly again. That bomber returned to drop more bombs. That investment continued producing returns. Germany couldn't afford this calculus. German bomber production struggled to replace combat losses. Pilot training programs were shortened as fuel grew scarce. Each aircraft lost mattered because replacements came slowly. Self-sealing tanks would have helped, certainly. But Germany lacked the rubber to build them and the production capacity to install them across an entire bomber fleet. So German aircraft flew with conventional fuel tanks, metal containers that leaked when hit, that caught fire when tracer rounds ignited vapor, that exploded when cannon shells struck just right. Luftwaffe bomber crews knew the risks. They flew anyway because orders were orders, and the war demanded their participation regardless of survival odds. The captured B-24 continued its journey to Rechlin, passing over Bavaria, approaching the testing grounds where Germany's aviation future was supposed to be secured through engineering excellence. But engineering excellence meant nothing when you lacked the raw materials to build what you designed. Test pilot Hans-Werner Lersch met the Liberator when it landed at Rechlin on April 4th. He would fly this bomber extensively over the coming months, evaluating its handling characteristics, performance envelope, defensive armament. He would write detailed reports praising American engineering, noting the aircraft's long range, heavy payload, and rugged construction. But he would also document what German engineers already knew. The self-sealing fuel tanks represented industrial philosophy fundamentally different from German approaches. America built adequate equipment in overwhelming quantities. Germany built excellent equipment in insufficient numbers. When those philosophies collided over European skies, numbers won. Rechlin's technical staff began their detailed examination. They removed access panels, photographed every component, measured tolerances, documented construction methods. The self-sealing fuel tanks received special attention. Engineers traced every layer, tested material properties, analyzed chemical composition. Their findings confirmed Hartmann's preliminary assessment. The tanks used natural rubber compounds unavailable in Germany. The manufacturing process required vulcanization techniques that worked only with specific material formulations. The entire system depended on supply chains that stretched across oceans Germany could no longer reach. One engineer, a chemist named Wilhelm Brenner who had worked with I.G. Farben before the war, wrote a separate technical memo that never reached official reports. He calculated exactly how much natural rubber Germany would need to retrofit self-sealing tanks across the entire Luftwaffe bomber fleet. 12,000 tons of high-quality natural latex, minimum. Enough to fill 2 cargo ships, enough to require 6 months of dedicated production from Southeast Asian plantations. Impossible quantities for a nation whose synthetic rubber production peaked at 70,000 tons annually, all of it needed for vehicle tires, industrial applications, and military equipment that couldn't function with substitutes. The mathematics of impossibility filled Brenner's memo. He understood what his superiors refused to acknowledge publicly. Germany had lost the war the moment Allied forces secured rubber supply chains, while German U-boats failed to interdict shipping lanes. couldn't build modern military aircraft without rubber. You couldn't protect fuel tanks without specific types of rubber that Germany no longer produced or imported. Every German bomber that burned when hit represented not poor engineering, but inadequate resources applied to impossible demands. The B-24 sitting at Rechlin demonstrated this reality in aluminum and rubber, a flying testament to industrial capacities that determined warfare outcomes regardless of tactical brilliance or strategic planning. Lersch flew the Liberator on April 7th, his first evaluation flight. He took the bomber up to 15,000 feet, testing its handling characteristics, evaluating control responses, measuring performance at altitude. The B-24 flew differently than German bombers. Heavier controls, less responsive, more stable in formation. Designed for mass production and crew survivability rather than individual aircraft excellence, it would never outmaneuver a fighter. It didn't need to. The purse, B-24, won through numbers, through self-sealing tanks that kept it flying after hits, through standardized parts that made repairs simple, through production rates that replaced losses faster than Germany could inflict them. The captured bomber spent weeks at Rechlin. Engineers documented every system, test pilots evaluated every aspect of performance, intelligence officers compiled reports that traveled up chains of command to Berlin. But all the documentation in the world couldn't change fundamental realities. Germany examined American self-sealing fuel tanks and understood exactly how they worked. German chemists knew the material composition. German engineers grasped the manufacturing techniques. But knowledge meant nothing without natural rubber to build them, without production capacity to install them, without strategic control of resources that determined who could field protected aircraft and who could not. The B-24's evaluation continued through spring 1944. Eventually it was transferred to the Luftwaffe's Venegono facility, fitted with German radar equipment, and used for night intruder missions against British bomber streams. A captured American bomber, operated by Germans, flying against Allied aircraft while wearing Luftwaffe markings. But its self-sealing fuel tanks remained American. The rubber bladders that kept it flying when German fighters hit it with cannon fire, that prevented fires from starting, that sealed bullet holes before fuel could spray onto hot engines. Technology Germany examined, understood, and could not replicate. The prisoner crews from the original B-24, captured when they bailed out over Italy, spent weeks in German interrogation centers. They answered questions about bombing tactics, target priorities, formation procedures. But when German intelligence officers asked about fuel systems and fire protection, the Americans just shrugged. They had no technical knowledge. They were pilots and gunners, not engineers. They knew the tanks were self-sealing because training instructors told them so. They had seen B-24 seconds with wings punctured by flak continue flying when conventional tanks would have leaked fuel and caught fire. That knowledge was sufficient for combat operations. How the systems worked, what materials made them function, those details belonged to rubber company engineers who would never see combat. Germany captured the aircraft, but not the industrial ecosystem that produced it. Rechlin's reports documented this gap with technical precision that made the strategic failure obvious. Self-sealing fuel tanks weren't complex technology. They were simple engineering backed by resource access that Germany no longer possessed. The Luftwaffe test facility near Berlin became a museum of captured Allied equipment. B-17 flying fortresses sat next to P-51 Mustangs. Spitfires shared hangar space with Soviet fighters. Each aircraft represented enemy capabilities that Germany understood, intellectually, but could not match industrially. Test pilots flew these captured machines, measuring their performance against German aircraft, identifying strengths and weaknesses, compiling data that might inform Luftwaffe tactics. But tactical advantages mattered less when strategic disadvantages rendered the entire comparison meaningless. You could know that American bombers used self-sealing fuel tanks. You could examine exactly how those tanks functioned. You could train fighter pilots to aim for different vulnerable points. But if America built bombers faster than you destroyed them, if rubber shortages prevented you from protecting your own aircraft the same way, if production capacity differences meant numerical superiority that overwhelmed tactical sophistication, their knowledge became irrelevant. The captured B-24 at Rechlin represented this reality in physical form. A bomber that Germany could fly but not build. Technology that Germany could understand but not replicate. Industrial capacity that Germany could document but never match. Hartmann completed his final evaluation report in June 1944. 50 pages of technical specifications, performance data, construction analysis. The section on fuel tank protection systems consumed 10 pages alone, detailing every aspect of the self-sealing technology with professional thoroughness. His conclusion was one sentence: replication, impossible with available materials and manufacturing capacity. The report circulated through technical intelligence channels, reaching desks of engineers and strategists who already knew what it would say. Nobody questioned Hartmann's findings. The mathematics were too obvious. Germany couldn't copy American self-sealing fuel tanks for the same reason Germany couldn't match American bomber production. Resources that determined industrial warfare outcomes existed in American factories and Southeast Asian plantations, not German planning offices. The B-24 that landed at Venegono in March 1944 flew operational missions for the Luftwaffe until late in the war, when Soviet forces advancing toward Berlin captured it at a damaged airfield. Russian troops discovered the bomber still wearing German markings, examined its American construction, and eventually scrapped it for metal. But during those months of German operation, the Liberator proved what Hartmann had documented in his report. Self-sealing fuel tanks worked. They kept aircraft flying after hits that would have downed conventional bombers. They saved crews who otherwise would have died in burning wreckage. They demonstrated industrial advantages that no amount of engineering skill could overcome through ingenuity alone. American rubber companies had developed the technology years earlier. Firestone, Goodyear, B.F. Goodrich, competing to create formulations that worked, testing materials against live ammunition, perfecting manufacturing processes that could scale to mass production. By 1941, American aircraft used self-sealing tanks as standard equipment. By 1944, over 18,000 B-24 Liberators flew with fuel protection systems, Germany examined but could not copy. The story wasn't dramatic. No brilliant German engineering breakthrough that almost changed the war's outcome. No secret weapon that could have shifted strategic balance if only resources had permitted. Just simple rubber technology, backed by industrial capacity and resource access, that determined which nations fielded protected aircraft and which nations watched their bombers burn. The rubber crisis facing Germany in 1944 extended far beyond fuel tank protection. Every military vehicle required tires. Every aircraft needed rubber hoses, oxygen masks, gaskets, and seals. Every ship used rubber components in dozens of critical systems. The Wehrmacht consumed rubber faster than German factories could produce synthetic substitutes. In 1940, Germany's total rubber consumption reached approximately 120,000 tons annually. 80% came from natural sources, imported through neutral countries or seized from occupied territories. By 1943, natural rubber imports had effectively ceased. Allied naval forces controlled shipping lanes. Japanese submarines could not reach European ports with cargo. Germany relied entirely on synthetic production that peaked at 70,000 tons annually, barely half what military operations required. American rubber consumption in 1943 exceeded 700,000 tons. Of this, over 400,000 tons went to military applications. Synthetic rubber production in the United States increased from 3,000 tons in 1942 to 756,000 tons by 1945. A 250-fold increase in 3 years, accomplished through systematic, industrial mobilization that prioritized resources, standardized processes, and scaled production using techniques developed specifically for wartime needs. The self-sealing fuel tank represented just one application of this rubber abundance. Each B-24 required approximately 300 pounds of rubber across all systems. Tires alone consumed 150 pounds. Fuel tank protection used 30 pounds of specialized natural rubber compounds. The remaining weight distributed across hundreds of smaller components, from oxygen system seals to hydraulic line insulators. Multiply 300 pounds by 18,000 B-24 seconds produced. Add similar requirements for B-17 seconds. Fighters, trainers, transports, and the scale of American rubber mobilization becomes visible. Over 2 million pounds of rubber just for B-24 production, separate from rubber needed for every other aircraft type, every military vehicle, every naval vessel. Germany couldn't match these numbers. Not because German chemists lacked knowledge of synthetic rubber production. I.G. Farben had pioneered Buna rubber development in the 1920s and 30s, producing commercial quantities before war began. But synthetic rubber from coal and limestone cost more to manufacture than natural rubber imported from plantations. Without access to Southeast Asian latex, Germany had no choice. Pay the higher costs or abandon rubber-dependent military systems entirely. The Auschwitz Satellite Camp, I.G. Auschwitz, housed synthetic rubber production facilities that consumed enormous resources while producing limited output. The plant never manufactured a single ton of rubber during the war, despite massive investments in construction and slave labor from concentration camp prisoners. After the war, Polish authorities brought the facility into operation, producing synthetic rubber using German equipment and processes that had proven functional in other locations. This production failure symbolized broader German industrial problems, resources diverted to facilities that never achieved operational status. Labor forced into projects that consumed materials without producing results. Strategic decisions based on engineering possibilities rather than resource realities. Meanwhile, American rubber companies operated at capacities that German planners had dismissed as propaganda exaggerations. Ford's Willow Run plant alone produced one B-24 every 63 minutes at peak efficiency. Each aircraft required rubber components that German factories couldn't manufacture in sufficient quantities, even if they had devoted entire production lines to the task. The captured B-24 at Rechlin became a teaching tool for Luftwaffe fighter pilots. Crews studied American defensive armament positions, learned blind spots where fighters could approach with reduced risk, practiced tactics against formations modeled on American bombing groups. But these tactical improvements meant little when strategic numbers overwhelmed individual engagement successes. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Test pilot Werner Lersche flew captured Allied aircraft more than any other Luftwaffe pilot. Over 120 different types passed through his hands at Rechlin. British, American, Soviet designs, all evaluated with systematic thoroughness that documented performance, handling, combat potential. His memoirs praised American engineering, particularly B-17 and B-24 bombers, that impressed him with their ruggedness and practical design philosophy. But Lersch never mentioned self-sealing fuel tanks in his published accounts. The technology worked too well, saved too many Allied aircraft, represented capabilities Germany could not match. Discussing it would require acknowledging industrial disadvantages that German propaganda refused to admit publicly. Better, too, praise American aircraft for their performance than explain why German bombers lacked protection systems that prevented fire after battle damage. The mathematical reality of rubber consumption extended beyond aircraft. German tanks required rubber for road wheels, track pads, and sealing systems. Each Panther tank used approximately 400 pounds. Each Tiger needed 600 pounds. Multiply these numbers by thousands of armoured vehicles produced, add requirements for trucks, artillery tractors, and supply vehicles, and Germany's rubber shortage became a logistics crisis that constrained every military operation. Synthetic rubber worked adequately for some applications, but failed in others. Tires made from Buna wore faster than natural rubber equivalents, requiring more frequent replacement. Seals degraded under temperature extremes. Hoses became brittle in cold weather. German engineers worked constantly to improve formulations, but chemistry imposed limits that ingenuity alone couldn't overcome. American forces operating in Europe noticed German vehicles frequently abandoned due to mechanical failures. Investigation revealed many breakdowns resulted from rubber component failures, seals that leaked, hoses that cracked, tires that disintegrated under combat conditions. Not poor German engineering, but inadequate materials applied to systems designed around superior natural rubber properties. The self-sealing fuel tank crystallized this materials crisis in aviation form. German engineers examined the technology, understood its principles, and recognized immediately that replication was impossible without natural rubber supplies Germany no longer controlled. Synthetic alternatives didn't work. You couldn't engineer around the fundamental chemistry. Either you had access to Southeast Asian plantations, or you accepted that your aircraft would burn when hit in fuel tanks. Luftwaffe bomber losses reflected this vulnerability. He 111 seconds, Ju 88 seconds, and Dornier, bombers that survived fighter attacks often died from post-combat fires started by relatively minor damage. A single machine gun bullet through a fuel tank could ignite vapors, spreading fire that consumed the aircraft before crews could bail out. Self-sealing tanks wouldn't have prevented all losses, but they would have saved enough aircraft to matter operationally. Germany attempted partial solutions. Some aircraft received additional armor around fuel tanks, adding weight that reduced performance without preventing fires. Engineers experimented with inert gas systems that flooded tanks with carbon dioxide to suppress combustion, but these added complexity and required components that other systems needed more urgently. Tank placement was optimized to reduce vulnerability, but designers couldn't eliminate fuel storage requirements without gutting aircraft range. None of these measures approached self-sealing tank effectiveness. American bombers took hits, sealed the punctures, and continued flying. German bombers took similar hits and burned. The difference saved American crews and doomed German ones, purely based on materials access that favored Allied nations. The captured B-24's operational career with the Luftwaffe lasted roughly 8 months. It flew night intruder missions, penetrating British bomber streams while German radar operators directed it toward targets. The Liberator's twin-tail configuration resembled British Lancaster bombers closely enough that Allied gunners sometimes held fire, mistaking the German-operated bomber for friendly aircraft in darkness. But even flying for Germany, the B-24's American-built fuel protection systems continued working. When British night fighters occasionally hit the captured bomber, its self-sealing tanks prevented fires that would have destroyed a German aircraft. The irony wasn't lost on Luftwaffe crews who flew it. They operated an enemy bomber superior to their own, not because of better aerodynamics or more powerful engines, but because American industry could source and manufacture rubber compounds, Germany could only examine and document. Post-war analysis revealed the full scope of Allied rubber mobilization. The United States government had established a rubber reserve company in 1940, stockpiling natural rubber before war cut off Southeast Asian supplies. When Japanese forces seized control of rubber plantations, American industry pivoted to synthetic production with systematic urgency that prioritized results over costs. University researchers, corporate chemists, and government scientists collaborated in ways that would have been impossible in Germany's rigid industrial structure. Companies that normally competed shared research findings. The petroleum industry provided feedstocks for synthetic rubber at controlled prices. Government funding eliminated financial risk that might have slowed development. Within 2 years, American synthetic rubber production exceeded pre-war natural rubber imports. By war's end, synthetic production had made the United States nearly self-sufficient in rubber supply. This accomplishment received less attention than atomic bomb development, but proved equally important to victory. Without rubber, military vehicles stopped moving. Without rubber, aircraft couldn't fly. Without rubber, self-sealing fuel tanks couldn't save crews from burning deaths. Germany attempted similar mobilization, but started from disadvantaged positions. G. Farben's Buna rubber worked well enough for many applications, but production capacity never approached demand. Coal and limestone needed for synthetic rubber competed with steel production, explosives manufacturing, and fuel synthesis. Every ton of rubber produced meant some other critical material went unproduced. Strategic decisions made years earlier compounded these problems. Hitler's autarky policies had emphasized self-sufficiency without ensuring sufficient production capacity for wartime consumption rates. When war began, Germany relied on stockpiles that depleted faster than anticipated. By 1943, rubber shortages constrained military operations across all theaters. The Eastern Front consumed rubber at rates that made replacement impossible. Vehicles operating in extreme cold required more frequent tire changes. Tank track pads wore through quickly on frozen ground. Fuel lines froze and cracked. Every mechanical failure reduced combat effectiveness, and many failures traced back to inadequate rubber components stressed beyond their design limits. Mediterranean operations faced similar constraints. Heat degraded synthetic rubber faster than natural alternatives. Hoses aged rapidly under desert sun. Tire blowouts became common. German forces fighting in North Africa experienced maintenance problems that American and British forces encountered less frequently, partly because Allied vehicles used superior rubber components that withstood environmental stress better. The self-sealing fuel tank represented just one example of how materials determined capabilities. American forces could field protected aircraft because American industry controlled rubber supplies. German forces couldn't, not because their engineers lacked understanding, but because resource access constrained what could be built regardless of technical knowledge. Rechlin's evaluation reports documented these realities with bureaucratic precision. Technical specifications listed material requirements. Manufacturing assessments noted production impossibilities. Strategic analyses calculated resource gaps. Every report reached the same conclusion. Germany could examine American technology. Germany could understand American engineering. Germany could not replicate American industrial capacity. Test pilot Löscher continued flying captured aircraft through 1945. He evaluated jet fighters, experimental designs, and enemy aircraft that fell into German hands. His final flight as a Luftwaffe pilot came in a Dornier Do 335 Profile, a push-pull twin-engine fighter that represented German aviation technology at its peak. The aircraft survives today in the Smithsonian's Udvar Hazy Center, a testament to engineering excellence unsupported by resources needed for operational deployment. That Do 335 used synthetic rubber components throughout because no alternatives existed. It flew well enough for testing, but would have faced maintenance challenges in sustained combat operations. Rubber seals would have degraded faster than natural rubber equivalents. Tires would have worn more quickly. Small failures would have accumulated into operational limitations that superior performance couldn't overcome. The captured B-24 never made it to American museums. Soviet forces scrapped it along with other Luftwaffe equipment when they occupied Rechlin in May 1945. But its contribution to German technical knowledge remained in reports that documented exactly what Germany lacked and why. Post-war interrogations revealed that German engineers had understood their disadvantages clearly. They knew American industrial capacity exceeded their own. They knew rubber shortages limited what aircraft could be built. They knew self-sealing fuel tanks saved Allied aircraft that would have otherwise burned. But knowing changed nothing when resources necessary to act on knowledge remained inaccessible. American technical intelligence teams, examining German aviation facilities after surrender, discovered extensive documentation on captured Allied aircraft. Rechlin's archives contained detailed reports on B-17 seconds, B-24 seconds, Lancasters, and dozens of fighter types. Every aircraft had been measured, weighed, photographed, and flown. Every system had been analyzed and evaluated. But these reports also revealed what German engineers could not accomplish. Annotations noted material shortages. Margin notes discussed production impossibilities. Summary statements acknowledged gaps between understanding technology and possessing resources to manufacture it. One intelligence officer, reviewing Rechlin's B-24 evaluation files, wrote in his trip report that German engineers had examined American self-sealing fuel tanks with scientific thoroughness that would have impressed American researchers. They understood the chemistry, the manufacturing processes, the material requirements. They simply lacked rubber to build them. His report concluded, German aviation technology was constrained not by engineering limitations, but by resource access. American industrial capacity determined the war's outcome more than any tactical advantage or strategic innovation. The self-sealing fuel tank embodied this principle. Simple technology, well understood by both sides, implemented only by nations controlling rubber supplies necessary for mass production. German aircraft burned when hit in fuel tanks, not because German engineers designed inferior systems, but because Germany lacked materials to build protection systems they fully understood. Final production statistics told the story in numbers stripped of dramatic narrative. 18,481 B-24 Liberators built, each using approximately 30 pounds of natural rubber just for self-sealing fuel tanks. Over 500,000 pounds total, excluding rubber needed for every other aircraft system. Germany's total natural rubber imports in 1944 approached zero. Synthetic production plateaued at 70,000 tons annually, shared across all military applications. No amount of prioritization could stretch limited supplies to protect all aircraft requiring fuel tank shielding. The mathematics were brutal in their clarity. America built bombers with self-sealing tanks because American industry controlled rubber supplies. Germany examined those tanks, understood their construction, and filed reports, documenting replication impossibility. Knowledge without resources accomplished nothing. The captured B-24 that landed in Italy during March 1944 became one more data point in this mathematical reality. German test pilots flew it. German engineers examined it. German intelligence officers compiled reports on it. But none of this activity changed the fundamental equation. Germany could not copy what it understood perfectly because understanding technology proved irrelevant without materials to manufacture it. Modern aviation historians, examining World War II, often focus on dramatic technological innovations. Jet engines, rockets, radar systems receive extensive attention. But self-sealing fuel tanks, unglamorous rubber bladders that prevented fires, arguably saved more Allied lives than any exotic technology developed during the war. American bomber crews owed their survival not to engineering brilliance, but to industrial mobilization that prioritized practical protection over theoretical performance. Self-sealing tanks reduced fuel capacity, added weight, complicated maintenance. But they saved aircraft that would have otherwise burned, keeping experienced crews alive to fly again, maintaining combat effectiveness that numerical superiority alone couldn't guarantee. Germany examined this technology closely enough to understand every aspect of its design and function. What German engineers couldn't examine was the industrial ecosystem that produced it. Rubber plantations in Southeast Asia, shipping networks across oceans, chemical plants processing latex into specialized compounds, manufacturing facilities producing tanks at rates that matched bomber assembly line speeds, government programs coordinating research across multiple companies while eliminating competitive barriers that might slow development. All of this existed outside German reach by 1944, not because of military defeats, though those mattered, but because strategic decisions made before war began had prioritized territorial conquest over resource security. Germany invaded Poland, France, the Soviet Union, seeking living space and industrial capacity. But none of these territories provided natural rubber supplies that determined whether aircraft burned or survived battle damage. The Rechlin evaluation facility closed in April 1945, when American bombers destroyed its runways beyond repair. German ground crews had already fled, taking whatever equipment could be moved, abandoning aircraft and documentation that couldn't be evacuated. When Soviet forces arrived, they found the captured B-24 among other Allied aircraft, all carrying German markings, all wearing evidence of systematic examination that had produced volumes of technical intelligence but changed nothing strategically. One final irony marked the B-24's German service. Its American-built self-sealing fuel tanks protected it during Luftwaffe operations exactly as they had protected American crews before capture. When British night fighters hit the bomber during its intruder missions, the rubber bladders sealed punctures, preventing fires that would have destroyed any German bomber. The technology worked for whoever flew the aircraft, indifferent to national markings or strategic allegiances. This functional consistency highlighted what German reports had documented. Self-sealing fuel tanks weren't secret weapons or mysterious technology. They were practical engineering backed by materials access. Any nation with rubber supplies could build them. Only nations controlling rubber supplies actually did. The war ended 3 months after Rechlin closed. Germany surrendered unconditionally, its forces exhausted, its industrial base destroyed, its strategic position hopeless. Post-war analysis would calculate that Allied bombing had destroyed approximately 1/3 of German industrial capacity, but materials shortages had constrained German production long before bombs began falling. Rubber shortages had limited tire production, reducing vehicle mobility. Fuel shortages had grounded aircraft and immobilized tanks. Steel shortages had slowed weapons manufacturing. Each shortage traced back to strategic decisions that prioritized conquest over resource security, that assumed quick victories would solve supply problems through territorial acquisition. Those assumptions failed when wars lasted longer than planned, when conquered territories provided less than anticipated, when Allied blockades prevented resource transfers from distant suppliers. Germany fought World War II with increasingly inadequate materials, supporting technically sophisticated weapons that couldn't reach their performance potential due to component failures resulting from substitute materials that never quite matched the real thing. Self-sealing fuel tanks crystallized these problems in aviation form. German engineers knew exactly what they needed: natural rubber, in specific formulations, vulcanized and treated according to American company specifications. They understood the chemistry. They could calculate the quantities required. They simply couldn't obtain the materials when Southeast Asian plantations sat 5,000 miles away behind Allied naval forces that sank any ship attempting the journey. The captured B-24, examined thoroughly at Rechlin, flew briefly for the Luftwaffe, then disappeared into Soviet custody, represented this resource failure physically. An aircraft Germany could operate but not build. Technology Germany understood but couldn't replicate. Industrial capacity Germany documented but never matched. Knowledge, it turned out, meant little without materials to apply it. Understanding how self-sealing fuel tanks worked accomplished nothing when rubber needed to build them remained inaccessible. German aviation technology achieved impressive sophistication while remaining fundamentally limited by resources that no amount of engineering brilliance could conjure into existence. American bombers kept flying after hits that should have been fatal. German bombers burned. The difference wasn't better American design or inferior German engineering. The difference was rubber, sourced from plantations, manufactured in factories, installed in aircraft by nations that controlled supply chains, determining who could build protected bombers and who could only examine them and document what could not be copied. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.